We will next aggregate several trees to form a forest of trees. The prediction of the random forest combines information from the predictions of the individual trees. In a regression setting, the prediction of the random forest is the mean of the predictions of the individual trees. In a classification setting, the prediction of the random forest is the mode of the predictions of the individual trees. Random forests introduce two types of randomness to decision trees. The first type has to do with introducing randomness to the data so that each tree is fit to a somewhat different data set. The second type of randomness has to do with which predictors are considered when making a split at any point in a given tree. These two steps have the implication of decorrelating the trees, which ultimately gives us a more reliable method. The first type of randomness in data, is due to bootstrap aggregation, which is often called bagging. Bootstrap is a resampling method which involves repeatedly drawing samples from a training set and refitting a model on each sample. If we have n observations in our training dataset, we form a bootstrap dataset by randomly selecting n observations with replacement from the original dataset. Because the sampling is performed with replacement, the same observation can occur multiple times in the bootstrap dataset. We can perform this process multiple times, and we'll likely get a somewhat different dataset every time. So bagging, in the context of decision trees, means that we draw a number of bootstrap datasets and fit each to a tree. The second type of randomness in how we split the predictor space, happens as follows. Normally with decision trees, we consider each predictor cut point combination when making a cut in the predictor space. In contrast, in random forest, each time we consider a split, we don't look at all predictors, but instead draw a small random sample of the predictors, and now we're only allowed to use these predictors when making a split. Each time we make a split, we take a new sample of predictors. This sounds really strange, but it's actually a very effective trick. Let's consider a simple example. We start from some dataset having 1,000 observations, and we have 9 predictors from x1 through x9. We want to build, say, 50 trees. So let's randomize the data first. We first draw 50 bootstrap samples from the original data and dedicate a separate tree for each dataset. We then fit the trees one by one. Starting from the first tree and the first cut, we first determine which predictors to use. If we're allowed to use, say, 3 predictors when making a cut, we might be allowed to use x3, x7, and say x8 for the first cut. We make the best cut we can, given the data and these 3 predictors, and we then move to the second cut in the first tree. This time we might be allowed to use predictors x1, x5, and x7, and again we find the best cut. We proceed until we fit the first tree, meaning until we fit whatever stopping criterion we have. We then continue the same way until we fit all of the trees in the forest. To make a prediction using a random forest, we identify the region in the predictor space separately for each tree where the test observation happens to fall. Based on this, we next have each tree make a separate prediction, and we then combine the predictions of the individual trees to form the prediction of the forest. So this is how random forests work. If you're not familiar with them from before, you may want to read more about them. Fortunately, using random forests in sklearn is easy.